Once again, ROC is an important property of Laplace transform, and there are two ways for us to do inverse Laplace transform. One of the ways is to do something similar to Fourier transform, so we can do this integral, or if we are doing something more fancy, we can think this integral as an integral in the S-plane. Okay, so it will be an integration from minus imaginary infinity to positive imaginary infinity. And how this integration depends on ROC is that, so there is a sigma parameter you can choose, and you need to choose sigma inside ROC. And that also means that you need to pick your this contour of your integral to be inside your ROC. Okay. And so this is integration, but most of the time we don't do this integration. Okay, sorry, let me check. Okay, so we're fine. Okay, and another way to do this inverse Laplace transform is that for rational function, once again we can do this partial fraction expansion. So for example, if we are lucky, then we can decompose our rational big X of S into this first order partial fractions. So linear combination of terms look like 1 over S plus A. And 1 over S plus A, we know that it can be inverse Laplace transform to two different possible time domain function, two time domain signal, depending on your ROC. So one of them is this e to the minus AT u of t, and another one of them is e to the minus AT u to minus I minus e to the minus AT u of minus t. So this is a right side signal, and this is a left side signal. And so which one of them you pick, it depends on whether the ROC is to the right or to the left of your pole. Okay. And so it's those two functions. One of them has ROC to the right of the pole, one of them has ROC to the left of the pole. And so if the ROC is to the right, you choose the right-sided function, and if ROC is to the left, you choose the left-sided function as your inverse Laplace transform. Okay. And from this, we see several examples. So we have this example, and C is three different ROC choice. So we have X of S equal to this 1 over S plus 1 times S plus 2, and a partial fraction expansion into this 1 over S plus 1 minus 1 over S plus 2. So it has a pole at minus 1 and a pole at minus 2, and then you can think about what is three different ROC give you three possible ways to invert this partial fraction of 1 over plus 1 and the partial fraction of minus 1 over S plus 2. So we have three examples to do these three inverses. Okay, so this is a quick review of what we go over this time. Okay, and now let's go to the day. So let's inverse Laplace transform, and let me see, we should be about 70. Okay, and we also talk about this geometric interpretation. That's saying that if you want to look at Fourier transform, you can think about how points on the j omega axis is close to a 0 or close to a pole. If you are close to a pole, then you will be very large. If you are close to 0, then you will be pretty small. Okay. And anyway, that's from this time. And today we are going to into a new topic. That's properties of Laplace transform. Okay. So this is very similar to all the previous chapter where we talk about Fourier transforms, and so we have a whole bunch of properties like those linearity, shifting property, conjugation, and differentiation. Okay. And but just like everything we talk about in Laplace transform, now we need to think about this is a different part, the part that's different from Fourier transform. Okay. So we see that at the very beginning. So this simplest example, we have this difference in ROC we need to think about. So in linearity, we have that if x1 linear Laplace transform to big x1, and small x2 Laplace transform to big x2, then we have a linear combination of small x1 and small x2 Laplace transform to this linear combination of big X1 and big X2. So this part is very familiar for all four different types of Fourier transform pair has this kind of linearity property. But now we need to think about how the ROC change when we do a linear combination between big X1 and big X2. So let's say big X1 has some ROC R1 and big X2 has some ROC R2. Then it's a linear combination of X1 and X2 has ROC. Now this is a very kind of complicated expression. So it's ROC will be containing R1 intersected with R2. Okay. So R1 intersected with R2 is pretty obvious. So you have some X1 component here and some X2 component here. And the X1 only converge on R1, X2 only converge on R2, and then you want to be converging. You want both X1 and X2 to converge, so you want to be on this intersection between R1 and R2. Okay, so this intersection of R1 and R2 guarantee that you will converge both on X1 and both on X2. And but why do we have this weird containing word here? Is because your ROC can actually be larger than this intersection. And then we will see an example of this happen. So what actually happen is that if you are very lucky or unlucky, then when you do this linear combination, some poles will cancel. Okay? So some poles between x1 and x2 will cancel. So for example, if your x1 is this 1 raised plus 1, and your x2 is this 1 raised plus 1 times x plus 2. Okay? And we choose the ROC to be both on the right hand side, so greater than -1, greater than -1. Okay, so we look at the pole-zero plot of those two things. So R1 is this thing. So x minus 1 is 1 raised plus 1 has a pole at -1, and this 1 raised x plus 1, x plus 2 has a pole at -1 and -2. But when you subtract those two functions, then you get this 1 raised plus 2. And you see this thing don't actually has a pole at -1. Okay? The pole at x minus 1 actually cancel out when you do this subtraction. Okay? And this thing only has a pole at -2. So the ROC will not be the intersection between R1 and R2, which is just greater or equal to -1. It will be extended from this R1 and R2 intersection. Okay? So let's start some drawing here. Okay? Basically, the ROC of linear combination of those two, because the -1 pole cancel out, and then we know because the -1 pole cancel out, so the ROC can extend. And in this case, we know the function does extend because the ROC does extend because this is a rational function, and we know the rational function ROC must be bounded by the poles. Okay? And since there is no pole at -1 anymore, so where am I? Okay. So since there is no pole at -1 anymore, so the ROC extend to this -2, and that's why, yeah. So the ROC, so the intersection was. So R1 R2 intersection was this part that was greater than -1, but because the pole at -1 cancel, so ROC extend to greater than -2. And so this is why we say containing. We know the R1 intersection with R2 must be inside ROC, but if you get very lucky, then some poles cancel out, then ROC can be larger. Okay, so this is what happened. Okay, is it okay? Okay, so you see that even in the very simple case of the linear combination, we need to take care of the ROC. Okay. So then now let's go to the next property. For those property, we almost skip all the derivation. So here we see the time shifting property. It's very similar to the Fourier transform case. So you shift time by a time t0, then you get this HR exponential term, complex exponential term in front of your S domain. So t goes to t minus t0, then you get this extra e to the minus st0 term in front of your big X of s. And ROC of this doesn't change, and it kind of makes sense because this exponential term, this e to the minus st0 term, will not create or cancel any poles, so ROC will not change. Okay, so this is a really simple one, and we also see that this is a complex extension of the time domain case. So in Fourier transform case, you have t0 here, then you get it's just become j omega, so you have e to the minus j omega t0 and big X over j omega. Okay, so this is just a complex extension of the Fourier transform time shifting property. Okay. And then we have shifting in time domain, and we can then think about shifting in S domain. It's a little weird here, so in Fourier transform I say it's a frequency domain, but S is a complex extension of frequency, so we just call it S domain. Anyway, so here you also get what you expected in the algebraic expression. So S change to S minus S0, and S0 can be any complex number. Then in a time domain, you get HRE to the S0t. Okay. But now we need to change ROC, because you think about you shift everything in S domain, then all the point 0 shift, then the boundary of your ROC should change shift, because well, for example, all the poles shift, and if you are a rational function, you are bounded by poles, then ROC should shift. Okay, so ROC shift to this weird function, ROC become it was R, and now it become R plus the real part of S0, where S0 is this shift. Okay. And so what's this meaning? Okay. And now the meaning of this, so this is actually a set, is that it is a set of point that's defined by, that's relative to this R, right? So what kind of point is inside this R plus real RES0 is that, so if you, okay, so keep saying RES0 is hard, so let's say it's R plus some number A. So, so this R plus A set is defined by a point is inside it, if only if that point is something in R plus A. Okay. So we written it in this more symmetric form. So some point is inside R if only if S plus A is in R plus A. Okay. So basically this R set is shifted by plus A totally. Okay. And I guess it's easier to see an example. So let's say, so we say the ROC is shifted by this RES0, or it's more like shifted by S0, but ROC only care about the real part. But anyway, let's look at the pole of X of S. Okay, so so why does this ROC need to shift? Is because say the X of S has some pole 0 at S equal to A. Okay. Okay, so when S equal to A, say this is a pole, then X of S is infinity. So we have a pole here. And now we think about X of S minus S0. So the corresponding pole will be at a point where S minus S0 equal to A. Okay. Because X of A equal to infinity, as we know from here. Okay, so and so when S minus S0 equal to A, this new function will have an infinity. Okay, and that happening when, so you move S0 to the other side, that's happening at S equal to A plus S0. Okay, so this pole at A become a pole at A plus 0. Okay, so you think so you see that the pole gets shifted by S0, and actually every point and yeah, so every point on this S plane actually shifted by S0, so your ROC gets shifted by S0. And for example, this bound here was some point R2, then it shifted to R2 plus the real part of S0, then this R1 shifted to R1 plus the real part of S0. Okay, and it's more like this point gets shifted by S0, but they only care about the real part, and this point is shifted by S0, and the boundary only care about real part. Okay, So that's the meaning of R shift to real part of R plus real part of S0 is that. Okay. So yeah, everything gets shifted by this S0, real part of S0. And an example of this is where the RC doesn't actually shift is we think about modulation. Okay, so if we have e to a j omega t modulated by x of t, then then here you can think about s is j omega, so it will Laplace transform to s shift by j omega. Okay. And so we see that this actually corresponds to a frequency shift in as a Fourier transform. So RC doesn't change at all because the real part of j omega is 0, and so everything is just shifted along the j omega axis. Okay. So every point 0 will get shifted by j omega in this example. Okay. And let's see the next property. This is time scaling property. Okay. So we multiply our t by some number a, and because t is real, let's say a is also a real number. And then we see this expression that's very familiar, very similar to what we have in the Fourier transform case. So here we have the corresponding Fourier transform property saying that x of at will Fourier transform to 1 over absolute value of a and the big S of j omega over a. And here you see this is basically exactly same thing, just j omega become s. So x of at will Laplace transform to 1 over absolute value of a and the big X of s over a. And but here the RC also need to change. Yeah. And remember we say that let's assume a is greater than 1, and we say if a is greater than 1, then we compress in time domain, and we will stretch in frequency domain. And so what happens is we need to change RC to this. So we want to stretch RC. So so a is greater than 1, and we want to stretch RC. Then we change into this new RC that's a times UR. Okay. And so we can think about different cases for a. So a can be positive or negative, and we can think whether absolute value of a is where the absolute value of a is greater than 1 or less than 1. So that will correspond. And whether a is positive or negative excuse me, whether a is positive or negative means that whether the RC flip left or right. Okay, so here we have some examples. So we have a starting RC from R1, R2, R1, and then we'll change to some AR2, AR1. So if a is between, so if a is between 0 and 1, then this AR2 and AR1 will be smaller than R2 and R1, so we'll compress the ROC. Okay. And it makes sense because when a is less than 1, then the time domain signal is stretched out, and the frequency domain or S domain signal get compressed in. And also when the absolute value of a is, sorry, not absolute value of a, when the value of a is negative, then it will revolve some reversal in S domain. So basically S domain will get the minus sign. Okay. And so in terms of ROC, that means the ROC will flip left and right. So let's say so when A is negative, so this R1 was on the right side, then AR1 will be on the left side. R2 was on the left side, AR2 will become the right side. So when A is negative, we'll get instead of in addition to this compression illustration, you will also flip the ROC left and right. Okay. And also from the time scaling property, we can get a special case that's a time reversal property that's very useful. And it says that if you get a minus sign on your x, then you also, get a minus sign on your t, then you also get a minus sign on your s. Okay. So this is a very symmetric relation. It's very nice. And also in terms of ROC, means that the ROC get a minus sign. So ROC become minus R. Okay. And since ROC are vertical strips, this just means the RLC will flip left and right, okay, around the J omega axis. Okay. So reversal about J omega axis. Although you think about what the meaning, okay, so let's talk something a little extra. So you think about what the multiplying a minus sign actually do in what does multiplying a minus sign actually do in a x-plane is actually rotation on 180 degree, or you flip around this origin point. So like this point will flip to like this point, etc. Okay, so this is what the minus sign actually do, and say this point will get flipped to this point. Okay, but because RC is a vertical line, then you only care about how does the vertical line change. Then the vertical line actually get flipped left and right. Although you are actually doing a point symmetry instead of a line symmetry around the geometric axis. Yeah. Okay, so but if you want to look at where the pole goes, then you need to be more careful. So so this is a bit of a digression. So if you think about there's a pole here, okay. So let's say if you had a pole here, and you do this time stretching, then the pole does not appear here. Okay, so the pole actually become here, something like this. Okay, because the pole get a negative sign, so it was a flip around this original point. Okay. Okay, everyone okay with this? This is time scaling property for Laplace transform. When your scale is a negative number, then you will get this extra time reversal. Okay. And so that's time scaling. And the next property is conjugation. Okay. Conjugation, once again, we want to look at the poles and zeros. Okay, we can say something about poles and zero. It's quite interesting. And anyway, conjugation property itself is, I guess, pretty clean. So it says, well, you have x of t Laplace transform to x of s, then x star of t will, so this complex conjugation of x will Laplace transform to big X conjugation, and also S conjugation. Small s will also conjugation. And so this is well, a bit different from for other Fourier transforms conjugation property. So Fourier transform conjugation property, we say we put a conjugation on bigger x and put a minus sign on s. But here is actually conjugation of s instead of just a minus sign, because before it was x star and Fourier transform to big X star of minus j omega. Okay, but you only get a minus sign here because S was purely imaginary. Okay, now S is a complex number, then this minus sign for purely imaginary S actually comes from a complex conjugation of the complex S. Okay, and so this is the formula, and actually the RC doesn't change. Okay. So you just a complex conjugation, whole bunch of things, and but complex conjugation of infinity is still infinity, and the complex conjugation of finite number is still a finite number. So the convergence doesn't change when you do this complex conjugation. So RLC is still R. Okay. And now we have this conjugation property. Then then we do what we usually do. That is, we look at the real function. So real function means that x of t equal to x star of t, and that means big X of x should equal to this x star of small s star. Big X star of s small s star. Okay. So this is what happens when things are real. And from here, then we want to write, we can derive a formula that's a little more handy, that you change the complex conjugation sign from here to here, then you have x star of s equal to x of s star. So when you do complex conjugation on your Laplace transform, let's say as you do complex conjugation on your independent variable. Okay? And what's the consequence of this is that you see that for real x, so for real small s of x, then big X of x has this symmetry on its 0, 0 and poles. Okay? And what do we mean by symmetry on its 0 and poles is that its 0 and poles basically should come in pair. Okay? Maybe it's easier to see an example first. So the 0 and the pole should come in pair. So if some point is a pole or 0, then its complex conjugation should also be a pole and a 0. Okay? I think it's easier to see here. And obviously, if it's real, then it's only on conjugation. So if this pole or 0 is real, then it just stay real. Okay? But if it's a complex number, then it is a complex conjugation, you will have a corresponding pole or 0. Okay? So it has a pole here, then it has a pole here. And if it has a 0 here, and it has a 0 here. So if it's a non-zero pole or 0, then it always comes in pairs. And here are two examples of real function and its complex conjugate. And so two real function and its Laplace transform that we calculated before. And we see the pole 0 plot does satisfy this property. So it has a pole, then pole 0, then its complex conjugation is also a pole 0. And we can derive this property from so this blue box formula we just said. Okay? So we think about, so it's this Henry squash here is the derivation. Basically these two lines are written in equation. So we think big X of some x0 is infinity or 0. So it's a pole or 0. If the pole is infinity, if the 0, well, obviously it's 0. Okay? And so it's this thing. Okay. And then we take a complex conjugation of infinity or 0, then we see that it is still infinity or 0. Okay? So this thing is equal to this thing's own complex conjugation. So we know x of s0 equal to x star of s0 because, well, we take a complex conjugation, infinity is still infinity and 0 is still 0. Okay? And then finally we use this property and we see that x star of s0 equal to x of s0 star. Okay, so then we see that if so from all those things string together, then we see that if x of s0 equals to infinity, then x of s0 star is also equal to infinity, and x of s0 equals to 0, then x of s0 star is also equal to 0. Okay, so that's the derivation. If you have infinity or 0 at some point, then you also have infinity or 0 at its complex conjugation. Okay. Are we okay? Everyone okay with this derivation? Yeah. And yeah, so geometrically it has this nice picture. So your pole and zeros always come in basic pairs. Complex pole and zeros come in pairs. Okay, and so that's the conjugation property and pole and zero structure of real function. And the next property is yeah, I guess this looks very nice. So it's I guess this is a little easier to remember, to memorize than the real property of Fourier transform. Fourier transform, we have that something like big A star equal to big S of minus S. But but here this pole and zero property looks a bit more geometric. Okay. And anyway, let's go back to, sorry for the going back, and now we can go forward to convolution property. So convolution property, as usual, it says that convolution in time domain give you multiplication in frequency domain. Yeah. And so the algebraic part is just very simple. So this convolution is the usual convolution as always. And then is multiplication of two functions. Well, although it's extended to complex domain function, but you can just multiply those two functions together. So nothing too weird happening. And then the RLC of this thing is similar to the RLC in linearity. So RLC basically needs to be intersection between R1 and R2. So R1 is the RLC for big X1, and R2 is RC for big X2. And but once again, now you multiply two functions together. Their point 0 can cancel out. So RC can extend from this intersection of R1 and R2. Okay. So it says RC containing R1 and R2, so it's at least this intersection between R1 and R2, but it can be made bigger. And here we have a very trivial example. So we have x1 is this s1 plus s plus 1 over s plus 2, with RC being the right hand side of this minus 2 pole. And so this thing only has a pole and minus 2, sorry, yeah. So RC being the right hand side of the pole, and S2 being S plus 2 over S plus 1, and RC also being the right hand side. But when you multiply x1 and x2 together, then you see that they exactly cancel out, because we say them so. And so since x1 and x2 multiplied together is 1, then 1 converge everywhere, and so RC obviously should be the entire S-plane, and so RC will not be an intersection between those two things. Intersection between those two things is greater than minus 1, but RC is the entire S-plane, because the pole at the minus 2 and the pole at the minus 1 both can cancel out when you do this multiplication, because this thing has a 0 and a plus 1, and this thing has a 0 and a plus 2. Okay. And so this is a convolution property. Once again, we see the RC can extend. Then next we have a differentiation property. And differentiation property is very clean. Okay, so it's just like basically the differentiation property of Fourier transform by just transform omega to S. So if you differentiation in time domain, then in a frequency domain you get the HYS. Okay, so it's even easier to memorize than the differentiation property of Fourier transform, and just get the HYS. And RC is once again something containing R, so basically R, but having HYS here can change the RC. And anyone want to answer whether the multiplying S might change the RC of this thing? In what case we will get a larger RC than R. Okay. How does the multiplying by S make the RC of S of big X, X times big X, larger than RC of X of S? Anyone want to answer? Why is the RC here not just R but containing R? Why? The only thing we do here is we change from X of S to S times X of S. You multiply things by S here. Okay, and I guess a hint is we just talk about multiplying two functions can extend the RC. So if x1 has a 0 at some place and x2 has a point at some place, then you multiply together, then point 0 can cancel out, then it will extend the RC. And a similar case can happen here, and anyone want to answer when does this S will cancel all the pole at the big X of S? Yeah. And anyway, so we can think S. So what is S? Well, S is also a polynomial. So we'll actually S when it equals 0, then S equals 0, right? So at S equals 0, is S has a 0, is a 0. And so that means if X of S has a pole at S equals 0, then this S equal to 0 then this S can cancel that pole out. Okay? So if X of S has a single pole at 0, at S equal to 0, then this multiplying S can make your RC larger. Then, so for example, maybe your X of S equal to like 1 over S and S plus 1. Then you multiply by S, then you become 1 over S minus 1 only. then your pole at s equal to 0 will get cancelled out. Okay, so this is usually what happens when RC gets extended is pole gets cancelled or subtract out, pole gets cancelled out when you change your S domain expression. Okay, and so yeah, that's completed. So you have rho part of S it was greater than 0, then now it should become rho part of S greater than -1. Okay, and then differential property. Okay, and here is a derivation of this. You can see it's a pretty straightforward derivation, and they actually use the inverse Laplace transform equation to do the derivation. And the inverse Laplace transform was this contour integral, and we do differentiation on both sides. Differentiation on t on both sides, and you see this side only depend on t on this e2st, and the e2st you do differentiation on t, you get hys, so you get hys here. Okay, and then we have so we now talk about differentiation in time domain, and we can talk about differentiation in the S domain. Okay. And the derivation is similar, so we have the Laplace transform equation, and we dds on both sides, and once again only depend on s on this e to the minus st, so you get the h minus t here. Okay. And so we see that in a time domain you get this minus t, so minus t x of t will Laplace transform to dbx ds. Okay. And RC is actually everything, and that's because differentiation will not increase or decrease, will not introduce or remove any poles on your function. Okay, and now we have a differential property, then we can derive something very useful that we already know we need to do. That we need to derive the inverse Laplace transform of the higher order poles. Okay. Remember for Laplace inverse Laplace transform of rational functions. Okay, so let's try go back. So those things we say we want to do partial fraction expansion, and just look up the formula to do inverse Laplace transform. But we give an example of only first order partial fractions. And to derive the inverse Laplace transform of higher order fractions, we need to use this differentiation formula. Okay, and we start with differential formula for the right-sided signal. So the RC was to the right side. Okay, and so we start with the first order fraction. So first order fraction, we have this this Laplace transform pair we derive in the first example of this chapter. Then we use differentiation formula, so differentiation on both sides, dds this thing, and then we get minus t, but because we know what's going to happen, we remove the minus sign to the other side, and we see that dds minus dds of this single fraction, single order partial fraction is a second order partial fraction, so this is 1 over s plus a squared. Okay, and yeah, and then as we said, the RC doesn't change. RC doesn't change at all, just R. So RC is still this right-sided. So now we see what is second order term or inverse Laplace transform into. So it is this same function but just multiplied by a t. This right-sided exponential decay multiplied by a t. And we can keep doing this, and and we will see that we can derive the third order term as a very similar thing, but we have a t squared term, t squared divided by 2. And in general, you can derive the nth order term. Here we skip the calculation. So nth order term, then you have this right-sided exponential decay, and then multiplied by n minus t to the n minus 1 divided by n minus 1 factorial. So basically multiplied by t to the minus 1. Oh, sorry, basically multiplying HR t to the minus 1 term. Okay, so So here we completed our inverse Laplace transform formula. I guess this is only for right-sided function, and then we also need it for this for left-sided function, but it can be derived similarly. Okay, and so now we know this higher-order partial fraction. Let's indeed do an example of inverse Laplace transform. So we have this rational function that's a pretty high order x of s equal to 2s squared plus 5s plus 5 over s plus 1 squared and s plus 2. So it has a second order pole at -1 and first order pole at -2, and the total is 3 poles. And we know when we do partial fraction expansion, it should have 3 terms. Okay, basically you have 3 order, you have 3 terms. So second order term for this s plus 1, and the first order term for this s plus 1, and the first order term for this s plus 2. So those 3 terms and 3 numbers here. And here where this give another number calculation, and so you can expand this out, and with 3 number here, and you see you want to match them, you can go get this 2 minus 1 and 3 here. Okay, so this is a partial fraction expansion of this rational signal, and then RC is still the same. RC here, RC was greater than -1, and here we have also greater than -1. Okay. And now, so we are in a very good case. So the RC is to the right of all 3 terms. So we can use the right-sided inverse Laplace transform for all 3 terms. And so the inverse Laplace transform to the 3 exponential decay term. And but the first term has second order. So in second order, so you get the HRT here. So the first term, so 2 becomes 2 here, and the second order term, so you get t equal to minus t. And the second term, you have -1, so -1 here, then this s plus 1 becomes equal to minus t. And then third term is 3, becomes 3 here, and s plus 2, because you have plus 2 here, you have equal to -2 here. And all 3 terms has RC to the right, so you have u of t. Okay. And as we said, if you have some RC to the left side of your pole, then you need to apply the left-sided inverse Laplace transform. And we don't do derivation here, but later in the table we'll include the left-sided signal for this thing. Okay. And let's talk about next thing. That's integration in the time domain. Okay. And integration in time domain is simple, but this is a bit tricky. Okay. And anyway, let's talk about this formula first. So you have integration from minus infinity to t in a time domain, and your Laplace transform to something very simple. It's 1 over s times the big X of s. Okay. And then RC is something funny. So I guess it's kind of the most complicated RC you have seen. So RC was RC is R. So the original RC of X of S intersection with RES greater than 0. Okay. And I guess there are several questions to us here. So R intersection with RES greater than 0 and also containing. So it can be this intersection but also larger. Okay. And so I guess now the question for you guys. So why do we need to intersection with this RES greater than 0 here when we get this extra 1 over S term here? Is it because you want to answer? Why do we need to have RC? So RC might be smaller than just the original R because RES, we have this extra RES greater than 0 term. Because we have this 1 over S is because this 1 over S might introduce the extra pole. Okay. And so the people want to answer whether this tetrapole of this 1 over A is introduced, is that is equal to how much? You want to answer? It's equal to how much? Take a guess. Where does the 1 over S go to infinity? Well, you say S equal to 0. Yeah. And so at S equal to 0, 1 over S equal to infinity. So this 1 over S term gives us a tetrapole at S equal to 0. That's why we need to take this intersection between R and IES greater than 0. Okay. So IES greater than 0 is RC of 1 over S. Okay. And it's a bit more complicated, but for now, because you might ask why is this greater than 0, not less than 0, that we'll present later. Okay. And anyway, so we have the intersection, but we still have containing. Okay. So containing means that it can be larger than this thing, and why does this happen? And okay, so this is a very convoluted logic. So why do we also have a containing here is because we say we introduce a pole at S equal to 0, but that tetrapole might get cancelled out by your X of S, because X of S might have a 0 at S equal to 0. Okay. So yeah, you might want to do this integration, but sometimes you might not need to do it, then it becomes containing. Okay, so anyway, that's RC of this part. And here we do a derivation. So derivation is a bit similar to how we do this thing for Fourier transform, but here we are actually more rigorous. Okay, so derivation comes from we know that the integration property always has a nice connection to this convolution with a unit state function. Okay. In Fourier transform, we also see that the Fourier transform of a unit state function can be derived from the integration property, and the integration property can be derived from the Fourier transform unit state function. Okay, and back then it was actually a bad loop because we don't know how to derive either of them from first principle. But here we already derived the Laplace transform of U of t. Okay, in example 9.1, we derived the Laplace transform for U of t because that's U of t is just exponential decay function setting a equal to 0. Okay, so in example 9.1, we already derived our U of t Laplace transform to 1 over S with IES greater than 0. Okay, and so from this we can derive our integration property by saying that integration is the convolution between U of t and X of t. And so this IES greater than 0 also tells us why we have IES greater than 0, not IES less than 0. Because we have seen that unit state function has this unit state function has this RC that's real part of S greater than 0 because it is right-sided signal. Okay, and that's that for now, and we'll continue more next class. Okay, let's take a 10-minute break.
House 按一下，我没了。数字不错哦，我们整个是。啊，再不够，那我再测个10。真他妈的不习惯。那我们开始这个做多了。你在扣扣的。他还没交。
他有给那个不是他有给一个数字。
哦。
他那边没有。只是延迟可能你的那个延迟在那里，才会。
那如果我们是说多了，觉得是一个不错的，然后再去想说，多了。
我觉得还是，我觉得我们原出版得赶快就是可能人要想好，就是说周期。不要，你这样会不会想搞多大？
确实。好，那我回去想一下，我确实是有一些比较好的想法，就是为什么我们去？
我目前那个
那我这个一定要交代。
好的，马上。
那我们呢？
在中间。
那我们的防御法一般一个关卡，我一般都是喜欢做大概15个左右的。一关我觉得，每一关差不多是上15。
可是如果是天软基本上对其对。
对啊，我是有个15个中，因为我是背对着你。
啊你知道是对抗的。
可是我们说好的。
哦，你说分两方。
这个是我们平常有交流的时候。
那么多吗？我印象那么多。
有问题啊？
我想问一下，就是最后这边，他说那，他说没有include，就是最后这边是什
么？最后是说，ROC 有没有include geometrics？geometrics 就是中间这一条嘛。就是说这3个东西只有其中一个东西，就是这3个function只有一个是有 Fourier transform 的。
所以只要没有含有geometry，
就 Fourier transform 就不会 converge 嘛，因为 Fourier transform 是相当于 Laplace transform 在 geometrics 上。那你 ROC 没有包含 geometrics， 就代表说在我们 geometrics 上面，你的这个 transform 不 converge， 所以就是你记过去了之后就记不出来，就变无限大之类的，对。
那你是说只有往右的那个，对吧？下去。
对啊。 但其实记不出来蛮正常嘛，因为这些都是一些很大的 exponential function 嘛，就想说也是一些 exponential growth 很快的东西，其实你去做 Fourier transform 那个积分，那基本上一积出来就是无限大嘛。所以我记得它是只有个就是都是 exponential decay 的 function 一积起来才是可以 converge 起来这样子。
反正没有答案就知道。对。下一个。没有，反正他们提出来就打这样，然后就是范围开始分段讨论。我们要不要看个图画呢？我不要加图画。
Hello. Okay. So let's go back to our properties of Laplace transform, and we have our integration property. And so we see that this ROC analysis of our integration property looks very similar to this ROC analysis of multiplication property. And indeed that's because the integration property can be derived from this convolution property. Okay, and so it's very similar to this convolution property in that its ROC is containing intersection of two ROC. Okay. And then the second ROC is the ROC for this unit step function. Okay. And I guess a bit of a digression here is that you look at this integration property and or you look at this unit step function Laplace transform, and you look back to Fourier transform property. And so if you still remember Fourier transform property, then you remember that Fourier transform property is something very weird. We remember that in Fourier transform that the integration property is not just the inverse of the differential property. It has this weird delta function term. Okay, so unit step function will Fourier transform to the 1 over omega term plus a weird delta function term. And then the integration property also have a delta function term. But instead, in the Laplace transform, you see that the integration and the differentiation has a very nice integration, and the and the differentiation has a very nice, reversal of each other. So this differentiation in time domain give you HRS, and then the integration in time domain give you 1 over s. Okay, and there is no delta function. And yeah, so that's something kind of weird between Laplace transform and Fourier transform. And I guess here we don't want to spend time in the detail, but it is something interesting that you can think about. Okay. But anyway, there is no extra delta function in the Laplace transform. It's just one race here. And we have extra slide that complete the derivation, but basically just we use the convolution property to see that integration is convolution between unit step function and our signal. And yeah, then in the frequency domain, you have this multiplication of 1 over s, and you have big X of s. Okay. And so that's the integration property. And next property we want to talk about is this initial and final value theorem. And I guess the motivation for this is a bit tricky, but for now we just motivate it as something that I can use to do check on your calculation. Okay, and anyway, this is now two totally new theorems. So in any of the Fourier analysis, you don't have this initial or final value theorem. So it's quite interesting, and it's so this initial and the final value theorem is used for very kind of a weird, or no, I guess not weird, but particular situation. So it's in this situation, actually we care a lot about us when we think about, say, we have some initial race condition. So a lot of the system we analyze is this kind of an initial rate system. So, or not initial rate system, sorry, initial rate signal. So we say our signal stay at 0, and at some t0 we start have a signal value, right? And then you can shift your things around, and say usually can shift things around, and say your thing actually start at t equal to 0. Okay. And so maybe the signal is the signal that looks like this. So its initial rate is 0, and it starts at some t0, and then your initial rate system will start to respond at this 0 plus point. Okay, and then this initial value theorem tells us how to find the initial value of your signal. So your signal at t equals 0 from your big X of s. Okay. And so it says that this x of 0 plus equal to you take a small s to infinity and s times big X of s. Okay. And this looks a bit tricky because there are a lot of infinity on your s plane, but actually because s is a plane, and infinity actually means for different direction, but usually they give you the same value. Okay, or at least in our example here, they should give you the same value. Okay, infinity is actually 1 point. And anyway, another motivation for this, you can think about your this x of t is actually, say, your h of t. Okay, so your impulse response for some system, and we know that for causal system, h of t will be 0 when t less than 0. Okay. So anyway, so initial value and the final value theorem, you will need this x of t equals 0 for t less than 0. Okay, and then you can get that x over 0 plus equal to x equal to infinity, s over big S of s. So this is the initial value, so you want to get the value of this small x at this 0 plus point where you start to have value. Okay. And also we also have a final value theorem, okay. And we still need this x equals 0 when t less than 0 condition. And then this final value, so value of x equal to t equal to infinity, this assuming this thing actually converges to something, and you will be this sen small x times big X of s, and value take s to the 0 limit. Okay, so this is the initial and the final value. Okay. and they want derivation, then it's in this homework problem of problem in textbook notation, textbook numbering is 9.59 and 9.53. Okay. And here we see an example of using initial and final value theorem to check that our Laplace transform is correct. So we have this example that we have e to the minus 2t u of t even plus e to the minus 2 e to the minus t cosine 3t u of t, and we want to check whether the initial and the final value of this thing can be derived from our s big X of s. Okay, and we already calculate big X of s, and when you multiply by s, then it becomes this rational function that's 2s cubed plus 5s squared plus 12s over s cubed plus 4s squared plus 14s plus 20. Okay. And so you want to check the initial and the final value. So initial value, you want to take this when s go to infinity. So you only look at the highest order term. So highest order term here is, well, the numerator is 2s cubed, and the denominator is s cubed. So you have 2s cubed divided by s cubed is just 2. So when s goes to infinity, then this thing becomes 2. And indeed, let's check out the initial value. So when t go to 0 plus, then this part give you 1, and this part give you 1, and 1 plus 1 equals 2. So you see initial value check out. And for final value, you want to take this thing when it goes to 0. So the upper term becomes 0 and the lower term becomes 20. You have 0 divided by 20 is 0. And indeed this thing should go to 0 when t go to infinity, because although the exponential decay part, exponential decaying part will always go make the whole function go to 0. Okay, is this example okay? Okay, so yeah, anyway, that's the initial and final value theorem. It can be used to check that your Laplace transform is calculated correctly. Yeah. Yeah, and here is a table talking about the properties that we already calculated. Okay, and also another table for Laplace transform pairs. And I think, yeah, so here we have something we did talk about, and I guess the thing that's very useful but we didn't derive is this thing. So it's inverse Laplace transform of higher order fraction when RC is left-sided. So we have this 1 raised plus a to the n, and with RC to the left side, then its inverse Laplace transform will be actually very similar, so similar to the first order thing. So first order, remember it was minus e to the minus at or minus t, and then we get the second trifactor. So we get the second trifactor, when we get higher order, we get this t to the n minus 1 over n minus 1 factorial term. Okay. And yeah, so it's the same as this trifactor. Okay, yeah, and here we also list all the first order term. So first order term, right-sided inverse Laplace transform to this, left-sided inverse Laplace transform to this, and the higher order term, when you have n greater than greater than 1, you get this HRT to the n minus 1 over n minus 1 factorial term. Okay, really simple to memorize. Okay, and yeah, we have also this sine and cosine, and sine and cosine can be derived from, I guess it's harder to derive. Oh no, yeah, sine and cosine u of t, those can be derived from the complex exponentials. Okay, can be derived from the e to the minus at. Okay, and also this s to the n and s to the n can be Laplace transform to u1. That's the nth order derivative of a delta function. And I guess this thing we cannot derive this is because we have the differential property. We have that one will Laplace transform to delta function, and so we have this Laplace transform pair. So one will Laplace transform to delta function. Then s to the n, you can just use the differential property. You have a HRS here, means that you get the HR differentiation on your time domain signal. Okay, that's the differential property. This thing. Okay, so that's everything. And now we go to next thing. So we use the property to analyze our LTI system. Okay? And now we use the LTI system now use the Laplace transform to analyze our LTI system. Okay? And so the start of the story is similar. So, so once again, we use the convolution property. So we know that in time domain, we have output y of t equal to x of t convoluted with h of t. So maybe I should have write it here. And so y of t equal to x of t convoluted with h of t. This is what we know since chapter 2. And now because of the convolution property, then we know that in the S domain, in the S domain, we have that big Y equal to big H convoluted with big X multiplying by big H. Okay, so this is just convolution property. And as we said, we have to do similar analysis when we have Fourier transform. But now the analysis is more complete because in the Fourier transform case, you need to make sure that all those three functions actually has a Fourier transform. Y of t and x of t, h of t all need to have a Fourier transform. And in particular, that basically means that h of t need to be a stable function. Means to correspond to a stable system, meaning that it's absolutely integrable. But now the Laplace transform is more free. You can have a lot of similarly diverging function to also have a Laplace transform, right? Because we have our ROC analysis. Okay, so something that's not convergent for Fourier transform can be convergent for Laplace transform just on some weird ROC. Okay, and I guess maybe we should go back to our starting example, right? So starting example was this example 9.1. We say that we have this e to the minus at u of t. Okay, and so Fourier transform only converge when a is greater than 0. But when we derive this Laplace transform, then we kind of say you can have whatever a here. Okay, this e to the minus at u of t, you can have a negative, then you will have your Laplace, you still have your Laplace transform. Okay, so say you have so you can have a negative, then you can still have this Laplace transform. Only say a needs to be a real number, and your RC will just to be your right side of your geometric axis, so you don't have a Fourier transform, but you still have a Laplace transform. Okay, so maybe let's draw it here. So this thing, when a is less than 0, then we just have our pole will have negative a, that's actually positive, and our RC will be right side of your negative a, and so RC don't include your geometric axis, but you still have the Laplace transform. Okay, and so that's one of the reasons why Laplace transform analysis is more powerful than the Fourier transform analysis, because you can analyze more systems, and we'll also see that we will get more property of our system from this Laplace transform of h of t. That is a big H of s, and the big H of s is called system function or transfer function. Okay. So in other course, you will see a lot of talking about system function or transfer function. Okay, And as we say, we want to know from this Laplace transform relation, we want to know the property of our system from this big H over S. And the two properties we'll talk about are causality and stability. Remember, we have done this thing in chapter 1 and chapter 2. In chapter 2, we analyze the causality and the stability from this small h of t. Okay, now we analyze this thing with big H over S. Okay, and so we start with causality. In chapter 2, we say that causality of a system is causal if only if your h over t equal to 0 for t less than 0. So your h of t only starts when t is greater than 0. And now we think about what's this thing, and we see this is a right-sided signal. Okay, because obviously, because you have a right-sided bound. So it has a right-sided bound at t equals to 0. Okay. And from here we see that signal is right-sided, and our RLC property says that the RLC for big H over S should be also right-sided. It means that it should extend to right infinity, and we for this extend to right infinity, we say include the right half plane. Okay, so includes a right half plane just means that your RLC extend to right infinity. Okay, so this is the property of causality. But unfortunately, this is actually not a if-only if condition. Okay, so this is very important here. A lot of properties so far we talk about these conditions are if-only if conditions. But this thing is only if condition. So, or in other words, if you are causal, then RLC is right-sided. But if your RLC is right-sided, it doesn't mean your system is causal. Your RLC is right-sided only means that your system is also right-sided. So, sorry, it's weird to say the system is right-sided. Your impulse function is right-sided. Okay. That's our RLC property tells us. So RLC is right-sided means your impulse response is also right-sided, but that doesn't mean your impulse response is causal. It might not start at 0, as we will soon see from an example. Okay, but if we have HR, okay. So this is very important. And another important property is that if you have HR property that your system is a rational system, then this is actually a if-only if equation relation. So if your system is actually, this big H of S is actually rational, then right-sided RLC give you a causal system. Okay. And let's start with some examples. So first example is, this is a function that we know and love a lot. This is exponential, right-sided exponential decay. So h of t equal to e to the minus t u of t. Okay. And we know this is just an example 9.1 with a equal to 1. So h of s is just 1 over s plus 1. Okay. And with RLC being right-sided, so RE of s greater than minus 1, point minus 1, and RLC is right-sided. And so indeed we see that this is a causal signal. This is a causal signal, so it only has a value when t is greater than 0. It's small h of t. And big H of t is right-sided and is rational, so everything checks out. Okay? Any question? So this is how to analyze causality from big H of S. Okay, and actually you only analyze it with the RLC of a big H of S. Okay, so RLC to the right, then and also rational, then you will have a causal function. And if you are a causal function, then RLC is to the right. Okay, and then let's see this counterexample of RLC to the right, and your system is not causal. Okay, so we have h of s equal to, now it's not a rational number, rational function is rational function times e to the s. So it's e to the s times over s plus 1. And once again, it has a point -1, and RC is to the right. Okay, and now we try to find what's the inverse Laplace transform of this thing. Okay, and we do this by using system property. And we see that this thing is very similar to the example we just talked about. Okay, so we have that 1 over s plus 1 will inverse Laplace transform to e to the minus tu of t. And how to go from 1 over s plus 1 to e to the s 1 over plus 1 is we use the time shift property that we talked about from this class. Okay, so shifting time. And so we use the time shift property, and it's this thing. Okay, so we say we shift by t0, then we get extra e to the s t0. Okay. So if we pick t0 equal to -1, then we have x over t plus 1, and we get e to the plus s here. Okay, and yeah, so if we apply this time shift property with t0 equal to -1, then we get the Laplace transform pair we want. We have extra e to the s here, and on this side we have e to the minus t plus 1 u of t plus 1. And since this is just a time shift of this exponential decay function, that we know how the time shift do. This is advanced function. Okay, so this is just advancing the h of t by 1 time step, and so now this h of t, this small h of t will look like this. Okay, so you just pull the whole function to the left by 1 unit. Okay, so h of t now is exponential decay starting at t equal to -1 by this this time shifting property. Okay, and now you see that this is not this is not an impulse response of causal signal, because from t equal to -1 and t equal to 0, our h of t has non-zero value, so this is not a causal system anymore. And bad. Yeah. So this is not causal anymore. And but you see that it is still a right-sided function. Yeah. So this is a right-sided function, but it's not causal because its starting point is not 0. It's not to the right of 0. Okay. So that's causality, and stability is I guess it's somewhat easier because you don't have so many cases. And also you see that stability can actually just be, once again, only analyzed with ROC. Okay, so ROC of h of s tell us stability, and the rational actually and sorry, so. And the logic here is pretty simple. So it's saying that if ROC include the geometric axis, then Fourier transform exists for your signal, for your small h of t, and then we also say that because h of t has a Fourier transform, then it's absolutely integrable. Okay, so let's write down the logic here. So ROC include j omega axis. Then we have Fourier transform of h of t exists. This this first equivalence we already know a lot. Okay, so if ROC includes geometric axis, so ROC of I should say ROC of h of t. Okay, so ROC of big H of s, sorry, not h of t, big H of s. If ROC of t of h of s includes geometric axis, then Fourier transform of small h of t will exist, because, well, we know geometric axis correspond to the Fourier transform, and it's in LC, so it's inside LC, so they all converge. Okay, and then from here we use this quite shaky relation that I think we also measure in chapter 4. Then we think that then this means that h of t is absolutely integrable. Okay, this is or I guess also this shaky relation we also we already do similar thing when we talk about LCK. So that's the first. Okay, I guess this is the full part. Okay, h of t dt is less than infinity, and let me see, we should around where here. So this is property. Okay, so this is also can be go from this property, right? We say some point is inside LC if only if this integration is finite. Okay. Wait, how do I? Sorry, this. Okay. So we say some schema point is inside LC if only if this integration is finite. Okay. And we have said that this is kind of a shaky derivation, but we think this is true. Okay. Yeah. And so if we take a sigma equal to 0, then it says that the j omega axis is inside LC, and if only if there is if only if this x over t is absolutely integrable. Okay. Everyone okay with this reasoning? And yeah, and remember in deriving 1.5 we have a kind of hand-wavy derivation saying that this is one of the Dirichlet condition, and this property 1.5 was derived kind of shaky, and now the derivation is still kind of shaky. So we can also go from property 1.5. Okay, and anyway, we know that LC of h of s include the geometric axis, means that h of t is absolutely integrable, and then from chapter 2 we know that this means system is stable. Okay, so that's logic here. So LC of h of s include geometric axis. Then from Fourier transform of h of t will exist, and that means that small h of t is absolutely integrable, and that means the system is stable. Okay, and so we string everything together. We see that LC includes geometric axis if only if the system is stable. System related to this big H or small h is stable. Okay, we're okay with the derivation. Okay, and yeah, so I guess a little bit of digression. So we also see that see from here that our analysis with this Laplace transform analysis can be applied to most LTI systems and Fourier transform analysis, because Fourier transform analysis only work on stable system, but now we can only work on stable system where the ROC include the j omega axis, but now we can also apply the Laplace transform analysis to non-stable system where the ROC doesn't include the j omega axis. Okay, but anyway, let's see some stability example. Soon we have some h of s look at this. So s minus 1 over s plus 1 and s minus 2. Okay, And now we can so a positive plot for this thing kind of look like this. So we have 0 and 1 at 1 from this s minus 1, and a pole from at minus 1 and plus 2. Okay, so it has this 3 pole or 0. So 0 at 1 and a pole at minus 1 and plus 2. And from this pole at minus 1 and plus 2, then we know that, and also this is a rational function, then we know that it has 3 possible RLC. So it can is RLC greater than plus 2, or RLC between minus 1 and 2, and RLC less than minus 1. Okay, and we can see it's and now we can see what's the time domain signal, the impulse response. So basically a time domain function for this time domain function small h of t look like for these 3 different RLC, and also see the system property that relate to these 3 RLC. Okay, and so first signal is, I guess we can kind of do a voting here. Okay, so basically we have these 3 RLC, and we talk about we can from RLC to determine where the system is causal or stable, and so we have actually six quadrants here. Okay, and so we can now do voting. Okay, and so for the first RLC, do you think it is causal or not? Okay. If you think this is causal, raise your hand. And if you think it is not causal, raise your hand. Okay. And and if you think it is stable, raise your hand. If you think it is not stable, raise your hand. Okay, so we are pretty good. And indeed, this is causal and not stable. Okay, and for causal is because the RLC is what I call right-sided, but the technical name is equal to right half plane. Okay, so extend to right infinity, and this is indeed causal, and and we can also check by direct inverse Fourier transform, inverse Laplace transform. Okay, so we can do partial fraction expansion is a factor on s plus 1, and factor on 1 over s plus 1, and a factor on 1 over s plus 2, and you will transform to this e to the minus t and e to the minus 2t, and e to the minus t and e to the plus 2t, and so this is 2 partial fraction. And then because the RLC is to the right side of both those poles, so both of those partial fraction will inverse Laplace transform to the right side signal. So they are both have this u of t. Okay, and just from this u of t, then you see that this thing is causal, because when t is less than 0, it's 0. And then is this thing stable? From the RLC analysis, we see that the RLC doesn't include the geometric axis, and so this thing should not be stable. And from the function here, the impulse response here, then we also see that this is not absolutely integrable, because you have this e to the 2t term, right? E to the 2t term is exponential in growing term, and obviously this is not absolutely integrable. You integrate it, you go to infinity. Okay, so this is not a stable system. Okay, and the next one. So if your RLC is between the minus 1 and 2, then you think it's a causal system. Then raise your hand. And you think it's not causal system, raise your hand. Okay, and if you think it's stable, then raise your hand. And you think it's not stable, raise your hand. Yeah, so we got it correct, very nice. And indeed, this is not causal because it's not right-sided, it is in between, and but it's stable because it includes the geometric axis. Okay, and so when we do the inverse Laplace transform, we get this signal. So because RC is to the left of this +2 and to the right of this -1. So this +2 term has inverse Laplace transform to a left-sided signal, and this -1 term inverse Laplace transform to a right-sided signal. So we see the signal is two-sided. It has a right-sided term and a left-sided term. And for t less than 0, it has this term here. So this is not causal. For t less than 0, it has non-zero value. But now we see that actually both of those terms are exponential decay. So this is a right-sided exponential decay function, and this is a left-sided exponential decay function. So both of them are exponential decay, and when you try, and so this is absolutely integrable. And when you try to do Fourier transform, both of those two terms will converge, and this is a stable system. Okay, and finally for this ROC of less than -1, if you think it's causal, raise your hand. If you think it's not causal, raise your hand. Okay, and if you think it's stable, raise your hand. And if you think it's not stable, raise your hand. Okay, yeah, everyone got it correct. So this is not causal and not stable because you get this two-sided, this two left-sided function as your inverse Laplace transform. Okay, and so this first function will be exponential going function to -infinity. So this is once again not stable. And then this whole function is negative t, so this is not causal. But we can give okay. Okay. Yeah. Okay. So this is yeah. So this is not not causal, but we give it h1n is called anti-causal, to mean that it has no value when t greater than 0. But this is kind of just a notation, not used too much. But when you see anti-causal, it means that when you say your system is anti-causal, it means that this impulse response only has only has value when t is less than 0. Okay, so that's anti-causal. Okay, and now we can think about a system that's both rational. Yeah, so we can combine all those properties together. So if we have a causal system, and it also has a rational system function h of s. Okay, and then we know the RC is to the right of the rightmost pole, right? Because RC needs to extend to the right, and it cannot contain any pole, so it should to the right of the rightmost pole. Okay, and now if we have the H-arc property, so we want it to be causal, rational, and also stable, then we know that the RC should also include the geometric axis. Okay. And so if we combine all those things, then we know this RC to the right of the rightmost pole should also include the geometric axis. And that means that this rightmost pole must be left of the geometric axis. Okay. So this is just combining everything we know and derive, and we arrive at this conclusion. So if our system is causal, rational, and stable, then always poles must be lying on the left of your S-plane. Okay. So all those poles must have a negative real part. Okay. So this is a nice property to know when you try to see your system function, determine the property of your system. Okay, so you can imagine that you have some kind of this detective problem saying that if your poles look like some distribution, then can you be causal, rational, and stable together, etc. Okay, and let's see more example of this. Okay, and so consider our system. our system that example we already seen. So our this exponential decay system. So h of t equal to e to the minus t u of t, and bigger h of s equal to 1 over s plus 1, and with RC greater than minus 1. Okay. And so this is both causal and stable. And you see indeed this only pole in the minus 1 is to the left of your j omega axis. Okay. And now consider a causal system with now exponential growing impulse response. So this is e to the 2t u of t. Okay. And let's also draw a picture here. So e to the 2t u of t kind of look like this, and this looks very unstable. Okay, because you try to integrate this h of t, you will diverge very fast. And in terms of h of s, in terms of pole zero plot S plane, so h of s, it has a point s equal to 2. Then from this point s equal to 2, you already know that you cannot be causal, rational, and stable, because this pole is to the right of your j omega axis. And indeed, what happened is that the RC is to the right of this plus 2, and this doesn't include the j omega axis, so your system is not stable. Okay. So the system, yeah, your system has a pole at this right side of your S plane. Okay. So that's an example of a rational system. How the causality and and stability related to your RC. Okay. And here is a slide for the as a reminder. So if your system is rational, then causal if only if your causal if only if your RC is right-sided. But if your system is not causal, is not rational, then then this first part is only one direction is true. So it's causal, then you are right-sided, but if right-sided is not necessarily causal. And for stability, we have if only if condition, so your system is stable if only if RC include the j omega axis. Okay, and I think that's all I want to talk about today. We can go back. So we talk about a lot of property of Laplace transform, and then we talk about how to determine the causality and the stability from the RC of our h of s. We see that this big Y equal to big H times big X is similar to this Fourier transform analysis, but it's more general because our big H, big X, big Y is whole S plane instead of just on j omega axis. So sometimes for some system where big H of j omega doesn't converge, you still have big H of S. And then previously we derive more Laplace transform pairs, and a very important tool is Laplace transform for inverse Laplace transform for those higher order partial fractions. It's 1 over s plus a to n, and we also derive a lot of properties for Laplace transform. See, this is a bit shorter than Fourier transform. We have a lot of them. And the important part is that now we have this extra column of RC. And yeah, so some of the transform will shift your RC, and also you can change your RC in some weird way. So we have this containing relation where we say the RC might be something intersection with something, and but the RC might be also bigger because some poles might get cancelled out when you change your Laplace transform. Okay. And yeah, so I think that's finished what we want to talk about today. So we'll talk about how to solve differential equation. Yeah, I think we'll also talk about differential equation. Yeah, on Thursday. So see you on Thursday. Okay. Yeah. Okay. So that's for today.